Hello everyone, welcome to tutorial number 3. So, let us start with question number 1. Here you are given that you have arbitrary sets A and B, and the sets A and B are such that this condition holds, namely A intersection C is a subset of B intersection C for any set C that you consider. If that is the case, then you have to show that A is a subset of B. Okay. So, you are given the premise that the intersection of A and C is a subset of intersection of B and C for any set C. So, since this condition holds for any set C, if I substitute C equal to A in this condition, then I get that intersection of A and A is a subset of intersection of B and A. But I know that intersection of A and A is nothing but the set A. So, that means I can say that my premise which I obtained by substituting C equal to A is that A is a subset of intersection of A and B. Right. Now, my goal is to show that A is a subset of B. Okay. So, for showing that A is a subset of B, I have to show that you take any element x in the set A, it should be present in the set B as well. So, I am taking an arbitrary element x and I am assuming it is present in the set A. And since I have established the premise that A is a subset of intersection of A and B, that means if since the element x is present in A, the same element x will be present in the intersection of A and B as well. Now, as per the definition of intersection of A and B, it means the element x is present in A and simultaneously it is present in B as well. That means definitely it is present in B as well. So, what I have established here is that if I start with an arbitrary element x which is present in the set A, I have established that it is present in the set B as well, and since x was chosen arbitrarily here, this is true for any element x that you choose from the set A, and hence I get the conclusion that A is a subset of B. Okay. In question 2, you are given the following. You are given 3 sets A, B, C such that this predicate holds for every element x in the set A, and the condition, the property here is that if x is in the set A, then the implication that x belonging to B implies x belonging to C is true, and this is a universally quantified statement. Okay. That means, this condition holds for every element x in the set A. Then you have to show, you have to either prove or disprove whether the intersection of A and B is a subset of C or not. So, in fact, we are going to prove this statement. We will prove that you take any element x which is arbitrarily chosen, and if it is present in the intersection of A and B, then it is present in C as well. So, we start with an arbitrarily chosen element x, and we start by reworking the premise that is given to be true here. Okay. So, the premise here is that this universally quantified statement is true for every element x. So, what I am doing here is I am rewriting this implication here. So, remember the statement P implies Q is logically equivalent to the disjunction of negation P and Q. So, that is why I have splitted this implication into a disjunction, and I get this equivalent form. Then I apply the same rule again over this implication. Okay. So, this implication is now replaced by this disjunction, and I put a negation here. And now you see everywhere I have disjunction. So, I can associate, I can apply the associativity property of the disjunction, I can club together the disjunction of the first 2 statements here. Now, what I can say is that the disjunction of these 2 negations is equal to the negation of the conjunction of these 2 statements. This is from the De Morgan's law. Okay. And again I can use the same rule that I have used here to replace this negation P or Q by P implies Q. So, this you can interpret as P this you can interpret as Q. So, you are given negation P or Q. So, I can rewrite it as that P implies Q. And now, what is this condition? This condition is nothing but it says that if x is present in A and if x is present in B, it implies x is present in C. So, if I since x was arbitrarily chosen, that means this condition holds for any x from the set A, and the condition that x belongs to A and x belongs to B simultaneously means x belongs to the intersection of A and B, and since x belongs to C as well, by the definition of subset, it follows that the intersection of A and B is a subset of C. So, this statement is a true statement. Now, in question 3 there are several parts and you are given a set S consisting of n elements where n is not 0. So, implicitly I am assuming here that n is greater than equal to 1, and now I have to count various number of various possible relations satisfying some properties. So, the first property here is I am interested to count the number of relations on this set S which are symmetric. Okay. And just to recall, the definition of a symmetric relation is that if you have the element or the ordered pair I comma j present in the relation R, then the ordered pair j comma I should also be present in the relation R. That is the requirement for a symmetric relation, right. So, what I have done here is I have drawn all possible n square ordered pairs, right. So, these are the ordered pairs in the set S cross S. So, you can have n square such ordered pairs, and any subset of these n square ordered pairs will constitute a relation over the set S. I have to find out how many ways I can take subsets of these n square ordered pairs such that the resultant subset satisfies the property of a symmetric relation. Okay. So, now among this n squared ordered pairs, I have highlighted this selected ordered pair. So, you can imagine this matrix, this is a n cross n matrix, and I am focusing only on the upper triangular portion of this matrix, and let A be any subset of the highlighted ordered pairs. Okay. So, the highlighted tuples I am calling it as H, and any subset of that I am calling it as A. My claim is that if you take the union of the ordered pairs in the subset A and the ordered pairs in A inverse, then the collection of these ordered pairs will give you a symmetric relation. So, say for instance, if you pick A is equal to say 1 comma 1 and say 2 comma 3, right. Say this is a subset of H, then A inverse will be the inverse of these ordered pairs. Inverse means taken by reversing or swapping the order of the ordered pairs. So, 1 comma 1 its inverse will be 1 comma 1, but the inverse of 2 comma 3 will be 3 comma 2. And now, if I take the union of these two relations, that will give me a symmetric relation. Okay. So, like that I take any subset A of the highlighted tuples, and to that I add all the ordered pairs which are found by taking the inverse of the ordered pairs in the set A, then the collection will be a symmetric relation, and that is the only way you can construct a symmetric relation over the set S, because the requirement for a symmetric relation is that if I j is there, if you have included I comma j, then you have to include j comma I as well. So, what I am intuitively saying is that in the set A you first decide what are the I comma j pairs that you are going to include. Once you have decided how many I comma j pairs you are going to include, just take the inverse of those I comma j pairs and the resultant union will give you a symmetric relations. Now, how many ways you can fix your I comma j pairs? Well, those I comma j pairs I am asking you to pick from the upper triangular portion of this matrix. Once you have fixed which I comma j pairs you are going to select from this upper triangular matrix, just take the inverse of those I comma j pairs from the lower portion of the matrix, and that will give you a symmetric relation. That means, I can say here that the number of symmetric relations that I can form is nothing but the number of subsets A that I can choose from the highlighted tuples. Okay. So, how many elements are there in the highlighted tuples? So, my claim is it is n times n plus 1 over 2. This is because in the first row you have n number of highlighted tuple, n number of tuples. In the second row of the upper triangular matrix you have n minus 1 number of ordered pairs, and like that in the last row you have only one ordered pair. So, if I sum these things I get n times n plus 1 over 2 number of ordered pairs, and how many subsets of these ordered pairs I can form, that is nothing but the cardinality of the power set of the tuples in your set H, and since the set H has these many number of elements, namely n times n plus 1 over 2, the number of subsets of these ordered tuples that I can form is nothing but 2 times 2 power n times n plus 1 over 2. So, that is the number of symmetric relations that you can form over a set S consisting of n elements. Okay. Now, in part B of the question I want to find out the number of relations over this set S which are antisymmetric, and just to recap, this is the requirement from an antisymmetric relation. If both A comma B and B comma A are present in the relation, then that is allowed only if A is equal to B. That means, if A is not equal to B, contrapositively if A is not equal to B, then you can't have simultaneously both A comma B as well as B comma A present in the relation R. So, now to count the number of antisymmetric relations, I do the similar thing here. I have drawn all the n square possible ordered pairs. Now, when you are trying to form an antisymmetric relation, the first thing to observe here is that the ordered pairs along the diagonal here can be either present or absent in your antisymmetric relation, right. That means, if say for instance 1 comma 1 and 2 comma 2 are included in your relation, then that does not violate the requirement of antisymmetric property, because if A comma B and B comma A are simultaneously present, then that is allowed only when A is equal to B, and all the ordered pairs along the diagonal elements have A is equal to B. Mind it, it is not mandatory that all the n ordered pairs along the diagonals should be present in an antisymmetric relation. Even if none of them is present, that is fine, that is still an antisymmetric, that still satisfies the requirement of an antisymmetric relation. The condition is that if at all both AB and BA are there, then A is equal to B. It is nowhere it says that for all AB, both AB and B comma A should be present in your relation for A equal to B, right. So, now how many ordered pairs I have along the diagonal? I have n such ordered pairs, and for each ordered pair I have two options, either to include it or to exclude it in an antisymmetric relation. Now, let us focus on the non-diagonal ordered pairs of the form I comma j and j comma I, where I and j are distinct. For instance, say n comma 1 and 1 comma n. Now, how many ways I can include these ordered pairs 1 comma n and n comma 1 and still satisfy the requirements of an antisymmetric relation? I have three possibilities here. Possibility 1, that neither I comma j nor j comma I is included in my relation R. So, for instance, I do not include 1 comma n and I do not include n comma 1 in my relation. That is fine, that still satisfies the requirement of an antisymmetric relation. Option number 2, that I include only I comma j in the relation, but exclude j comma I. Remember, I can't have both I comma j as well as j comma I in my relation, because I am considering the case when I is different from j, and if I is different from j, then as per the property of an antisymmetric relation, both ordered pairs I j and j chi are not allowed to be included. So, I have only three possibilities: include none of them, or include I comma j, or include j comma I, right. Now, how many such I comma j and j comma I pairs I have in this matrix where I and j are different? Well, I have n square minus n over 2 number of such I j and j I pairs. This is because there are total n square ordered pairs, and from them I am excluding the elements along the diagonal. So, I am left with n square minus n number of pairs, n square minus n number of elements, and if I pair them in the form I comma j and j comma I have to divide it by 2. So, for every such pair I have three options, right, and the possibility of including or excluding I j j I pairs is independent of the possibility of including or excluding the ordered pairs along the diagonal element when I am forming an antisymmetric relation, right. So, that is why the total number of ways of forming an antisymmetric relation is how many ways I can consider the elements along the diagonal, which is 2 power n, and how many ways I can consider the remaining elements, and that is 3 power n square minus n over 2, and if I multiply them, that will give me the total number of relations which can be antisymmetric. In part C of third question, you are supposed to find out the number of relations which are asymmetric, and this is the requirement for an asymmetric relation. If at all A comma B is there in your relation, then B comma A is not allowed in the relation. This does not mean that this should be true, this does not mean that for every AB you should have either AB or BA present in the relation. It is fine if none of them is there in your relation R. Okay. So, again I do the same thing here, I consider n square ordered pairs and see how many ways I can select subset of these n square ordered pairs and still satisfy this universal quantification. So, the first thing to observe here is that now none of the elements or the ordered pairs along the diagonal are allowed in an asymmetric relation, because if you include I comma I, then that violates this universal quantification, because you have both A comma B as well as B comma A present in your relation. So, that is not allowed. So, none of this, so 1 comma 1, 2 comma 2, I comma I, n comma n, none of them are allowed in an asymmetric relation. Now, let us focus on the remaining elements, and again let us club them into pairs of the form I comma j and j comma I, where I and j are distinct, and again it is easy to see that for such I comma j and j comma I pairs, I have 3 possibilities here. I can include none of them and still my relation will be asymmetric. I can include I comma j and exclude j comma I, or I include j comma I and exclude I comma j. Okay. So, I have 3 possibilities here, and how many such pairs you can have? N square minus n over 2 such pairs. So, as a result, since I have to definitely exclude the diagonal elements, the only possibilities I have now is to consider the non-diagonal elements, and with respect to non-diagonal elements I have these many options. So, these are the total number of asymmetric relations. In part D, I am interested to find out how many relations I can form which are irreflexive, and the definition of irreflexive relation is this. It states that for every element A in the set S, A comma A should not be there in your relation R. That means now none of the elements, none of the ordered pairs along the diagonal are allowed, because that will violate this universal quantification. Whereas, if I take any other tuple I comma j where I and j are different, then I can either include them or I can either include it or exclude it. That won't violate the requirement from an irreflexive relation, right. So, for instance, if n comma 1 is present in my relation, that is fine, that satisfies this universal quantification, and I can have n comma 1 as well as 1 comma n both present there, that still satisfies the requirement for this from an irreflexive relation, right. So, how many such I comma j ordered pairs I have here? Excluding the if I exclude the diagonal elements, I am left with these many ordered pairs, and for each such ordered pair I have 2 possibilities, either include it or exclude it. So, that is why the total number of irreflexive relations is 2 power n square minus n. Part E, I now want to find a number of relations which are simultaneously reflexive as well as symmetric, and the requirement from a reflexive relation is this, and the requirement from a symmetric relation is this. So, if I consider the ordered pairs, I have no choice, but I have to definitely include all the diagonal ordered pairs, because I have to satisfy the reflexive property. But apart from this, apart from the ordered pairs along the diagonal elements, I have the choice I have the choice with respect to the elements or the ordered pairs which are not there along the diagonal. So, I consider all I comma j and j comma I pairs where I and j are different. So, I have now two possibilities. I can choose to exclude both I j as well as j I, that still satisfies the requirement of a symmetric relation, or if I decide to include I j, then I am forced to include j I, because if I include only I j, but exclude j I, then that will violate the requirement of a symmetric relation. So, with all such ordered pairs of the form I j and j I, where I and j are different, I have two possibilities. And how many such I j and j I pairs are there? Where I and j are distinct, I have n square minus n over 2 such pairs. And since I have no option, no choice with respect to the diagonal elements, I am forced to include them. The total number of relations which are both reflexive and symmetric is nothing but 2 power n square minus n over 2. The last part of the question, I have to find out the number of relations which are neither reflexive nor irreflexive. Okay. So, not reflexive means this universal quantification should be false. That means, at least one element A should be there in the set S such that A comma A is not present in the relation, then only this universal quantification can become false. And not irreflexive means this second universal quantification is false. That means, you have at least one element A in the set S such that A comma A is present in your relation, then only this universal second universal quantification can be false. Okay. So, if I consider this n square ordered pairs, then what I can say here is that since my set S is non-empty. So, I stress I assumed here n is greater than equal to 1. So, since my set S is non-empty, I can't have a relation which is simultaneously reflexive as well as irreflexive, right. It can't satisfy both. It can't satisfy both the requirements of a reflexive relation as well as irreflexive relation, because reflexive relation says that you should have all the elements along the diagonal present in the relation, whereas the irreflexive property demands that none of the ordered pairs along the diagonal should be present. So, you can't have both these conditions occurring simultaneously in the relation R. So, I have to exclude all the elements along the diagonal, right. It turns out that if I try to find out the number of reflexive and irreflexive relations simultaneously with respect to the options that I have for the non-diagonal elements, then the counting might become slightly tricky. So, instead what I do here is I find out the number of relations which are either reflexive or irreflexive and subtract it from the total number of relations which I can form over the set S. What I know here is, since I can't have a relation which is simultaneously reflexive as well as irreflexive, then I can confidently say that if I subtract out the total number of relations which are either reflexive or irreflexive from the total number of relations, that will give me the required answer, because there will be no overlap which is possible here. No overlap in the sense there can't be any relation which is simultaneously reflexive as well as irreflexive. So, my goal here was to find out the relations which violate the requirements of being reflexive and irreflexive. So, to do that, what I do is I find out the relations which have one of these two properties, that means it is either reflexive or irreflexive, and subtract out the number of such bad relations from the set of all possible relations which I can have over the set S. The number of total number of relations which I can have over the set S is 2 power n, and if I subtract out the number of reflexive relations which is 2 power n square minus n, which we have calculated, and the number of irreflexive relations which also is 2 power n square minus n, then that will give me the total number of relations which are neither reflexive nor irreflexive. Now, let us start question 4. Again we have several parts, and here again we are given a set S consisting of n elements, and I assume here n is greater than equal to 1. I have to find out the number of relations which are symmetric, antisymmetric and reflexive. Okay. So, these are the requirements from my relation. My relation should satisfy the property of a reflexive relation. My relation should satisfy the property of a symmetric relation, and my relation should satisfy the property of an antisymmetric relation as well. Okay. So, I consider the ordered pairs, n square ordered pairs. So, since I want my relation to be reflexive, I have no choice, but I have to compulsorily include all the ordered pairs along the diagonal here. Now, I consider ordered pairs of the form I comma j, where I is different from j, and try to see what I can do with these ordered pairs, so that my resultant relation is both symmetric as well as antisymmetric. Okay. So, in order to maintain the symmetric property, if I decide to include the ordered pair I j in my relation, then I need to include j I as well. But as soon as I include I j and j I in my relation, it will violate the requirement of an antisymmetric relation, because antisymmetric relation says that if your I and j are different, then both I j and j I cannot be present in the relation, right. So, that means these two conditions cannot occur simultaneously. That means, if I have ordered pairs of the form I j, where I is different from j, I am not allowed to include such ordered pairs, because that will violate the requirement of symmetric and simultaneously antisymmetric property. So, that means I have now only one way of forming the relation, namely I just include all the ordered pairs along the diagonal, and that is all. That relation will be symmetric, antisymmetric and reflexive. Apart from that, I can't do anything else, I can't include any other ordered pair. So, that is why the total number of relations which satisfy these three properties simultaneously is 1. Part B, I have to find out the number of relations which are symmetric, antisymmetric and irreflexive. So, let me write down the requirements. Irreflexive means no ordered pairs of the form A A should be there. Symmetric means if A B is included, then B comma A should also be there, and antisymmetric means if you have distinct A and B, then either A comma B or B comma A should be there, not both of them. It is fine if none of them are there. So, again I consider the n square possible ordered pairs here. Now, since my relation has to be irreflexive, I have no choice, but I have to compulsorily exclude all the ordered pairs along the diagonal elements, all along the diagonal. Okay. Now, what about the ordered pairs of the form I j, where I and j are different? So, again if I want to include I j, then to retain the symmetric property, I have to include j I. But since I and j are different, if I have both I j and j I present in my relation, then it will violate the requirement from an antisymmetric relation. That means, again here with respect to the ordered pairs I j, where I and j are different, I am not allowed to have the ordered pair I j, because if I try to include I j, then it will either violate the requirement of symmetric property or antisymmetric property. And since the diagonal elements are also not allowed to be included, it turns out that the only relation which I can form, which is simultaneously symmetric, antisymmetric as well as irreflexive, is the empty relation, namely include no ordered pair. That means, none of the ordered pairs among these n square ordered pairs should be there in my relation. Then only my relation can have all the three properties simultaneously, and that is why there is only one relation possible. Part C of the question, I have to find out the number of relations which are both symmetric and antisymmetric. So, this is the requirement from a symmetric relation, and this is the requirement from an antisymmetric relation. Okay. So, now if I consider the elements the ordered pairs along the diagonal, for each ordered pair I comma I can either choose to include it in my relation or exclude it in the relation. That will satisfy both this universal quantification. That means, if I decide only to include 1 comma 1 in my relation, that is fine. That does not violate the requirement from a symmetric relation, or it does not violate the requirement from an antisymmetric relation, because antisymmetric says that if A and B are same, then fine, you can have both AB and BA present in the relation, right. And mind it, I am not enforced to have all the ordered pairs along the diagonal to be included in my relation. I can just select any subset of them. Okay. What about the ordered pairs of the form ij where I and j are distinct? Again, if I decide to include ij, I am forced to include ji to maintain the symmetric property. But since I and j are distinct, if I can't have both ij and ji simultaneously present in my relation, because that will violate the antisymmetric property. So, again the conclusion here is that for every ordered pair of the form ij where I and j are different, I am not allowed to include them. That means, the only options I have is with respect to the diagonal ordered pairs, and I can take any subset of the ordered pairs along the diagonal that will satisfy the requirements of a symmetric and antisymmetric relation, and how many such subsets I can form? I can form 2 power n such subsets. So, these will be the total number of this will be the number of relations which are simultaneously symmetric as well as antisymmetric. So, with that we end our tutorial number 3. Thank you.